that down. Let's go like this. Participants mute. Let's go here. Let's go here. Sign in. Wow. Okay, come on, let's go. Memory serves me. Okay. Calculus, yes. The very, very bottom. Chapter 2. 90, oh, 105. Random, that's fine. And let's just change that to 105. We can do 81 first. All right, let me share my screen. Start the broadcast. Optimize the video, okay. We'll start here. No real announcements. Hope everyone is doing well. We are in the home stretch. So next week is gonna, I'm under the impression that's our last, next Wednesday, a week from today will be our last live session. Now is a good time to get caught up on any late or missing assignments. Idealistically, the goal is like, you want to finish everything so that when you go to take your final, when you finish your final, you should be done. All right, so you can anticipate the final. If next Wednesday is our last meeting period, then that Thursday and Friday is the reading period. That Sunday, so a week from this Sunday, the final should become available. The hard deadline for all assignments is that Friday, May 9th at 11:59 p.m., right? So, okay. As usual, if you have questions, feel free to unmute yourself or type in the chat. We'll do our best to get it addressed and resolved. And I think we're going to start with question 81, actually. This is from chapter 2. Number 2. Okay, anyway. Let's see what we got going here. Let's minimize that. And let's I'll just read this off. I know it might be a little bit small, but this comes from section 2.5, question 51. I think that's social sciences. The population of a country dropped from 51.3 million in 95 to 47.5 million in 2007. Assume that the PFT, the population in millions, T years after 1995, is decreasing according to the exponential decay model, okay? Find the value of K and then write the equation. Estimate the population, okay. So estimate the population of the country in 2018. After how many years would the population be? 1 million according to this model. Wow, 1 million, okay. Let me, I'm gonna have to take some notes. Let me get a screenshot. And we're gonna hop over to Notability. So 1, 2, all right. Right, we're looking good. And my goal is to have you all's grades updated by Monday. If I haven't updated grades by next Wednesday, then I'll just take some time during class to update it. It should pretty much, honestly, now that I think about it, I think I automated all of that. So whatever's in Blackboard, it should be accurate because I don't think there's anything for me to manually come back and do. So it's a good idea to go ahead and check your grades in Blackboard. Make sure that like assignments that you completed are showing up, that the grade looks accurate. If it looks out of order, just let me know and I'll manually go through and check it. But I just realized that I did automate you all's grades and it should be showing up in Blackboard. So I'll just check it and make sure that it's behaving properly. Okay, it said that this data is modeled to fit the exponential decay model or is designed to fit the exponential decay model. Let me grab. So we're going to use the exponential decay model. Let's see. So A of t, we we can say like A naught e to the negative kt exponential to k. Now let me see. And so we're gonna let 95 be year 0, right? We're gonna let 95. So I'll just put in parentheses. This is year 1995. The population was 51.3, and the units here are millions of people. And then, so at 95 to 2007, what is that, 12 years later? It went to 45.7 million people. Okay, so we have these two pieces of information, and we want to fit them to this exponential decay model. Let's see. So I think the first question asks us to solve for k. Okay, so the starting population, we're going to let it be the 51.3. That's when time was 0, right? So that's our starting population. So we got this 51.3 e to the negative. We don't know k. Now the time, it's been 12 years later, so we're going to say 12k, like this, equals, what, 45.7 million people. So we have one equation, one unknown we can solve, right? All right, so we can divide both sides by that 51. 45.7 over 51.3. Now, if you're crunching numbers along the way, and if you calculate a number along the way, you gotta write out the long decimal. Otherwise, it's not gonna work, right? Or keep it exact. I tend to keep mine exact. If you crunch a number along the way, you gotta write out the long decimal every time and only round at the end. Okay. So then we're gonna take the natural log on both sides. Oops, I'll fix that in just a moment. Okay. So now on the left, we have this negative 12k. On the right, we have this natural log of this 45.7 over 51.3, okay? So then ultimately, we get something like k equals negative natural log of this guy, whatever that number is, divided by 12, okay? Then we're going to use a calculator. Okay. So again, that the k that you see right now, that's my exact answer. Then I'm going to use my calculator to get my approximation. So negative natural log 45.7 divided by 51.3. I can type today. All divided by 12. So, you know, it takes practice. You got to get your parentheses proper. I went a little overboard on my parentheses, but it's fine. All right, so we get this k. We get approximately so less than 1%. I feel like something's off. That's the decay rate. Might be negative. I don't know about this. We're gonna try it. If it doesn't work, we got some things that we can augment. All right, so let's see if we can find the one that we were working on. Let's see. Population. Okay. P naught e to the negative kt. Okay. Okay. It looks like it's what, C? So find the value of k. Does it say round to 4 decimal places? Let's try C. That looks similar to what we have. We can get it to work. Let's see, turn that off. One, two, so 0096. Okay. So so now we have we confirmed that the K is correct. So then the population of the country in 2018. So the year zero was what, 95. So then 2000 was 5 years later. So what is that, 23 years later? So we plug a 23 into that function. Let me think how I want to do this. Okay. So what I'll do this 51.3. Let me see. Actually, what I'm doing, I'm gonna store that as alpha A. Right. So it's just capturing that long decimal. Then I'm going to go to my y equals. Did I use this? No. Then I'm going to put 51.3 times e to the power of a times x. All right, because remember, we just stored that decimal into a. Okay. So now I'm going to call on that function. I want to evaluate that function. What do we say? 23 years later when x is 23. And it says round to one decimal place as needed. So 64 million. All right, 64. And so that little technique that you saw me use was like with the storing, let me see, around the one decimal places. Now, one other thing I could think is sometimes the rounding is a little bit weird. So what I can do is instead of putting a, just put 0096 x and try that. And see, then that takes it to, it still takes it to 64. 23, right? 23 years later. Is it 23? 95, 2000, so 18 and 5. Mm-mm. Because both of those round to the same number. Okay, let me go to my y equals. Oh, I think I see my error. I'm missing my negative. I'm definitely missing my negative. That's what it is. Right here, negative a x parentheses and delete. Delete. Guess I gotta keep going. Yeah, we were missing a negative. Okay, so let's try this one more time. All right, 41.1. Let's try 41.1. Okay. According to this model, blank years after 95, the population will be 1 million. So we want to set our function, set it equal to 1. Now, I think it does a solver. Let me see. If I go to math, solver. I don't know how to use this. Let me, I'm going to try to use that here, though. How to use solver, TI 83 plus to solve an equation. Let's see. I didn't really. Okay. To solve an equation, some more. You can use the solver feature, blah, 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 blah. Enter the equation, example. Enter a guess. Solve. Alpha, enter to execute the calculator, find the solution, review the solution. So step one, access the solver, enter this equation, press enter for a guess, example 0, and then press alpha, enter. X equals this or this was the solution. Let me see if I can get that to work first, and then I'll switch to ours. Access the solver, okay. Equation solver, equation 0 equals, okay, so they have like x squared minus 5x plus 6. Okay, I'm gonna hit enter. Let me just hit, oh, alpha enter. Let me see. Press enter and enter a guess. Let me try like 0. Bound. Press alpha enter. I might need to go back. Let me quit. Let me go back to math. Enter. Alpha enter. Nothing. Press enter, and then I guess press alpha enter. X equals, which is solutions. Missing something here. Let's quit. Let me go to math. Okay, let me go back up. Come on. Okay. Come on. Access the solver. We did that. Okay. If there's a previous equation, press the up arrow to clear it. Enter the equation you want to solve. It should be rearranged so that one side equals 0. Make sure to use the appropriate variables. Okay. Press enter. After entering the equation, it will display x equals initial guess. Can be any number. It's a starting point for the solver. Press alpha enter to execute the solver. The calculator will find the solution. Okay, let's see if we get it to work. So, okay, I think that's good. I'm gonna hit enter. I'll do a guess of like 2. I'm just gonna hit enter. Okay, I'm gonna hit alpha enter to solve. I don't know, I can't get it to work. Alpha enter. Maybe left, right equals 0. There's something that I'm missing. I'm probably gonna let this go. Let me try 0. Alpha enter. Oh, that's not right either. We're so close. Like I know we can do it. There's a video. Come on. And then my device is like lagging. I don't know why it's lagging. So let's see if I can find. We can go to second matrix. I know matrix solver. Solution using numeric solver. Let's see if this one works. With pictures. Okay, that's the one I want. Go back. Oh, I didn't want this to take so long. Where'd it go? This one. Let's try this one. Okay. I know that's a different one, but that's okay. They set it to 0. That's fine. Math. All right. Program. Alpha. Solve. Yeah. Well, how do we get that? Type in the equation. Type X. To use powers, complete the rest of this equation and press enter. Press alpha, then enter. Math. Yeah, unplug this. Maybe that's why it's moving so slow. Yeah, it's really going slow. Sorry, guys. Alpha solve. Left. -1. Let's try 0. Enter. I'm going to set this to like, can I change this bound? No? Yeah, I can't get it to work. Yeah, I don't know what I'm missing. Okay. Well, anyway. And it's like, that's the thing that's arguing me. And my device is kind of like lagging a bit. Okay, I'm going to have to let this go because it's eating up too much time. Free math solver. No, that's not what I want. Anyway, okay. So we want to be 1 million. Long story short, we want to set this guy equal to 1 and solve. I'll just obviously it took way longer. I was kind of hoping we would get it because then it would be something else that we could use. But at least you know it exists, and if you just kind of dig and try, eventually you'll get it. We got our A naught, we got our K. We said when, so we're trying to solve for T. Okay. So we have this 51.3 e to the negative. I'm going to reference K, and we're trying to solve for T. And we want that to equal 1 million. So I'm just going to use the K that I had from before. Divide both sides by 51. So we'll have this e to the negative kt equals 1 over 51.3. Take the natural log on both sides. Okay. So then, long story short, the time is going to be the natural log of 1 over 51.3 divided by, it's going to be a negative here, whatever that k value that we have. Okay. I think we still have it saved. I'm going to get rid of this. I just couldn't, let me see if I hit alpha enter here. No. But if I did like x equals, let me see, alpha. Okay, so we still have the k stored. So then if we look at time, we're going to do negative natural log of 1 over 51.3 divided by alpha A. That's our K. About 409 years. Sorry that took so long, guys. Like I said, I was trying to see if I can get this over to work. Nearest whole number 409. Okay. All right, let's try another one. Generate 49 is fine, actually. I think my device needs to be like restarted, but I don't want to eat up more time. This comes from section 2.3, question 21. Find the equation of the tangent line of this graph. There is this the linearization thing? So the derivative of the function when x is 10 is going to give us our slope. I mean, we can do it manually. There is a function, like if you want the equation of a line, it's called the linearization. Let me see, I'm gonna click on view an example, see if they use it. No, I think they're doing it manually. Okay, that's fine. Okay, we can do it manually. That's fine. I'm gonna write it out. I need to get a copy. I don't even know why it's moving so slow today. Let's cut, paste. Okay. Equation of the line tangent to the graph when x is 10. So for instance, if we start with like the equation of the line, y equals mx plus b, right? So we need to find our slope and our y-intercept. The y-intercept occurs when x is 0, so we can do that first. It'll be something that's simple. It looks like we'll have a slope and a point, right? Okay, well, we can't start with the y-intercept, but we can go ahead and find the slope. Let me think. Let's go ahead and find, so if our f of x is this what, natural log of x quantity cubed. So let's go ahead and find f prime, 3 natural log of x squared all over x. Right? So times the derivative of the outside function times the derivative of the inside function. Then we want to evaluate this when x is 10. So then f prime of 10 is going to be 3 times the natural log of 10 quantity squared over 10. That's going to be our slope, right? Whatever that number is, right? We're just going to leave it as is for right now. So now we have a slope, and then we can find the point, right? So when x is 10, we can find the corresponding y. So let's go ahead and find f of 10, right? So natural log of 10 cubed, like this, right? That's going to be, so we'll have an x, we'll have a y, and we'll have the slope. We can use the point slope form, right? So point slope, I mean, honestly, we can use y equals mx plus b, right? If we're going to use y equals mx plus b, the slope is there. I'm just going to put it as is for right now. So this 3 times the natural log of 10 squared over 10 times our x is 10. We're trying to solve for b, and the corresponding y is that natural log of 10 cubed, right? At this point, we have one equation, one unknown we can solve. So the long story short, our b is going to be equal to natural log of 10 cubed minus 3 times the natural log of 10 quantity squared over 10. Okay, I guess it would cancel, right? We can cancel those 10s. This 10 would cancel this one. So then our b should be equal to that. Hopefully this makes sense. Let's see, where'd it go? So I'm going to do natural log of 10 quantity cubed minus 3 times the natural log of 10 quantity squared. So we get that for our b. I'm going to store this as alpha b just to save it. Store, not that one. I want to store that as alpha b. Our slope. Okay. Find the equation of a line. Okay. I want to store the slope as well. So we have this 3, let me think about it. There it is. 3 times the natural log of 10 quantity squared divided by 10. We get an answer. I'm going to store that as alpha m for our slope. Hopefully that doesn't mess me up. Okay. So we have our y-intercept. We have our slope. So then the equation of the line, let's see. We're going to get something like y is going to be approximately 1.59x minus 3.7. Again, it's an approximation. So that should be the equation of the tangent line at that point. Again, the derivative gives us the slope. We can find the corresponding y by plugging in 10 into the original. So then we'll have a point and a slope. We can either use the point slope or we can use y equals mx plus b like we did. Let's see if let's see if this is accurate. It should be. I don't see why not. Top here says slope intercept. Okay. So again, get this to work. Okay, our slope that we got was 2 decimal places, so 1.59 x minus, let's see, 697, so it's minus 3.7. Okay, let me check on you guys' Zoom real quick. I know you guys tend to be mute. I could change that, but it's okay. I'd rather it does kind of help to keep the flow, but it would help more. You all would be better off if you talked more, but I'm not gonna force it. But yeah, whoever does the most talking does the most learning. That's the only reason I know this stuff is I talk about it so much. So if you're like quiet and passive, it's a lot harder for stuff to get through, but it's okay. Let's go to 83. Why are you keeping it so close in the 80s? Let's go to 83. Okay, we'll go here. All right. Let's see. For this scatter plot on the right, determine which, if any, of these functions might be used as a model for the data. Let's see. It could be exponential. It could be quadratic. Probably the one on the left. Not quadratic. It's not logarithmic. I would go exponential since that seems to be. It could either be. I mean, it could be quadratic. All right. I would go exponential. Let me see, what are my options? Oh, we got a good amount of options. Exponential growth, right? I think it's between either D or E, and I'm going to go with E. Let's try E first. Okay. Oh, that was it. Yeah, because it is behaving like an exponential, but you could fit it to a quadratic if you wanted. It's just it depends on like the nature and like what kind of model you wanted to fit, how you think it's going to behave in the long run. Okay. Generate. We can go to question 25. Yeah, I'm totally distracted. Like I'm just thinking about all sorts of things. Take the derivative. Well, E is its own derivative times the derivative of the power. So that's just going to be E to the power of 15x times the derivative of 15x is just 15. So I'm going to put the 15 over here. So 15 times E to the 15x. All right. Easy peasy, lemon squeezy. Generate. Let's go to question 75. 75. Right there. Did you all get a chance to see Sinners? Man, that was a good movie. If you haven't got a chance to see it, go watch it. I'm not going to spoil it for you. At least I don't intend to. I don't even like to say it was a good movie. I don't like to hype movies up, but anyway, it's free marketing for them. The amount of carbon-14 present in animal bones after 2 years is given by this. A bone has lost 13%, okay, of its carbon-14. How old is the bone? So we're basically solving for T. We're gonna, let me see, the amount, so 14% remains. So if it started with 100%, it finishes with 13, it's lost 13, so it finishes with what? 87%? Okay, and then solve for T. So we can let this, and instead of percent, we could put like a 1. Like say it started with 100% and it lost 13%. So it's going to finish with 80 or 0.87. Take the natural log. I think I'm going to take my notes here. So the natural log on both sides and divide by that number. Okay. Matter of fact, I don't know what number we were. Did I change? Okay, I think we're good. It keeps jumping around. Anywho. So again, we're gonna assume that it starts with 100% and then it fell to 87%. We take the natural log on both sides. So we'll have what? The natural log. I'm gonna do 0.87 to represent 87% years divided by this negative, that number. Man, it's a long number. 0.0000123 12097 12097. Okay. Nearest integer. Carbon 14. That's reasonable. 1151 years. Okay, what time is it? Okay, let's do some more. I'm gonna get rid of this and generate. Let's go to question 39. We'll go to question 39 right here. So let me see. It says this equation gives the balance at the tiers of an initial investment of $8,000, which pays 5.5% compounded continuously. Find a formula for D of A, the D of A by dA by dt. Let's see. I guess we just take the derivative. It's going to be itself. So basically, it's going to be that formula times 0.055. I think what they want you to write though is like 0 point. Like the whole point of this one is that rate times the original function, right? Find a formula. But we can just say 0.055 times that to give the original formula, and it should work. Okay, let me get this number here real quick. 8,000 times 0.055. Okay. So 440 and then everything else. 440 e to the power of 0.055 t. See if that works. Yeah. A prime of 5. Balance after tiers. So the rate of change after 5 years. Okay. So let's say that 440 times e to the power of 0.055 times 5. Nearest dollar is 579. So 579. The account is growing by $579 per year after 5 years. Dollars increase in the total amount per yearly increment event. Years per dollar increase. It's not dollars, it's not years. Dollar increase in total amount per dollar increase in the initial investment. Per yearly increase in investment time period. Why does it seem so strange the way they're wording it? I'm gonna go with the first one. Okay. I'm under the impression that that's like after 5 years, the account is growing by $579 per year. And that rate's going to change each year, right? Because it kind of feeds back on itself. But after 5 years, the account is growing by almost $600 per year. And this was that long. Let me see. Interpret. Okay. Let's see. The future value of a 5-year investment, 8,000 at 6.5. 6.5%. Where's that 6.5 coming from? The future value of, I feel like it's C. The future value of a 5-year investment of $8,001 will be this, more than the future value of a 5-year investment of this. Oh, let's see. So at year 6, future value of investment will be more than the future value. More than the future value of a 5-year investment. Oh shoot, and they don't have a view on example either. Let me see. The future value of a 5-year investment of this will be at 6.5. No, I don't think that's it. 5-year investment of $8,000 at 6.5. That percentages throw me off. I'm like, no. The future value of a 6-year investment of $8,000 will be 5-year investment of $8,001. Again, what part is this? Find and interpret A5. Okay. So the account should be growing by $579 per year after 5 years. Investment of 8,000 will be more than the future value. The future value of a 6-year investment will be of 8,001 will be, that just feels off. More than the future value. Okay, 579. I'm gonna go with C. I'm not really sure. 579. Let's see, units to the previous step. Okay, let's try it here. I might have to see their explanation on this one. Okay, so we got it. It says the future value of a 6-year investment of $8,000 would be $579 more than the future value of a 5-year investment at that amount. Okay, so basically the next year, how much more you'll get. So then A of 6 minus A of $5 per year around the 2 decimal places. Okay, so then what I'll do here, I'll put the original, let me see. Yeah, I'll put the original here and my Y equals, I'm gonna go 8,000 times E 0.055 T or X, right? And then basically I'm just gonna say F of 6 minus F of 5. So when X is 6 minus when X is 5. 2 decimal places. So 595.5. Hot 595.5. You know, that's what it sounds like a radio station. 595. Come on. 595.5. Let's see. Okay. All right. Well, that was an adventure. We still got a good amount of time, so we're gonna keep the party going. Let me just check on you guys in Zoom real quick. You guys look okay. I don't see any notifications or anything. Who we got here? Let me see. Okay. All right. People showed up, so we're good to go. Let's keep going. Let's generate. Let's go to question 29. Let's see what we got going here. 29. Right here. Looks like we need to use quotient rule. Okay, I'm going to write this one out. Copy. I'll try to include the question ID, so if you reference this, you'll at least know where in the textbook it comes from. Okay. All right, there should be enough space down here. Okay. All right. Oof. So low D high minus high D low over low low, right? So quotient rule. Bottom times the derivative of the top. E is its own derivative times the derivative of the power. So that's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay. Now it looks like we can. They both have what? It looks like we can factor, right? It looks like we can factor out. They both have a 2. E. Let me see. Okay, they both have a 2x to the power of 7, e to the power of 2x. Right? So then in this first one, it looks like we have an x here. Minus, that's gone. There's a 4 left, minus 4. So then this 7 turns this guy into a 9. And so that means that all of this is gone. So then now we have 2 e to the 2x times x minus 4 over x to the power 9. Okay, let's see. E to the 2x, x minus 4, x to the 9. 2e to the power 2x times x minus 4, x to the power 9. Okay. All right. Let's generate. Let's go to back in the 80s. For whatever reason, it's living the 80s today. We did 81. We could do 82. I think actually, I think I want to try this one actually. I might have to use my viewing example, but let's give it a go. This one says a coroner arrives at a murder scene at 8 p.m. She finds the temperature of the body to be 83.1 degrees Fahrenheit. She waits for an hour, takes the temperature again to find the body temperature to be 79.4. She knows that the room temperature is 65 degrees Fahrenheit. Assume that the temperature of the body was 98.6 degrees Fahrenheit when the murder occurred. When did it happen? Let me think. Do we need Newton's law of thermal cooling? Let me think. She arrives at the scene at 8. So at 8 o'clock, the temperature was 83.1 degrees Fahrenheit. She waits for an hour. So that's at 9 o'clock. It's 79. She notes that the room temperature is 65. Assuming that the temperature of the body was 98 when the murder occurred. Okay, I'm going to attempt it before I look at the viewing example. Only thing that's throwing me off, how do we factor in the temperature of the room? And I think the temperature, you have to subtract the temperature of the room or something like that, but that's the only thing that's throwing me off. Everything else I think we got. Give me a moment. Let me think. Let me kind of write some stuff first. I want to attempt it without looking at it. Again, I'm not sure how to factor in the temperature of the room. I think you have to subtract it, but like I said, I'm not 100% sure. Let me just look at it. Come on. All right. That's the only thing that's throwing me off. Aside from that, I think we have the rest of it. Too slow. Oh, I lost it. Nope, that's not what I want. Hmm. Okay. Let me just write down what we have so far. So at 8 p.m., she arrives, and the temperature is 83.1 degrees Fahrenheit. And at 9 p.m., it's 79.4 degrees Fahrenheit. Okay. The room temperature, 65 degrees Fahrenheit. Okay. And I'll just say normal temperature is 98.6 degrees Fahrenheit. Does it drop exponentially? Do we do the exponential decay model? Let's see if that works. Let's just try. So something like temperature of the body based on time, T naught times e to the negative kt. We need to subtract the room temperature in there somewhere. That's the only thing. Give me just a moment before I look it up. I'm about to look it up. I think we know that the initial temperature of the body is what, 98.6 degrees Fahrenheit. We don't know the time. Yeah. I'm gonna have to look at it. The only thing I'm not sure is how to factor in the temperature of the room. That's the only thing that I'm spending time on. So what I'm gonna do is do an example, and it'll show us plus C. Let me see. Yeah, Newton's law of cooling, right? Okay, that's fine. So we do need to change it up a little bit. $65. Okay. So the initial temperature of the body, it should be 98.6. Let me see. So they added the plus C for the temperature of the room, right? And then if the initial temperature, she finds the temperature of the body, she arrives at 9. So if that's when time is 0, 82. Where did she use the 82? Okay. Okay. Okay, I think we got it. So the main thing we need is this Newton's law of cooling, this A times e to the negative, basically the exponential decay plus C. Okay, I think I got it. Let's give it a go. Let's hop back over here. So we're gonna check one more thing. Yeah, we're fine. Okay. So I'm gonna T A times e to the negative kt plus C. So let me see. The C is the temperature of the room. Let me think. Hang on. At time 0, we know that that's the no, that's not right. I'm still missing something. Replace T with N for the number of hours since the murder was committed, then determine the value for A using initial values, right? So whenever the murder happened, the temperature of the body was 98.6. So then they get an expression for A from there. Okay. Okay, that's fine. Okay. So, whenever the murder happened, right, the temperature of the room, we're going to assume that it was still the 65 degrees Fahrenheit, okay? And the temperature of the human body is 98.6. Okay. So we're trying to solve for the constants of what, A and K, all right? So this will give us A. We're going to have e to the power of 0 is a 1. So then subtract 65. A is going to be whatever that is. 33.6. Okay. So then at this point, now they said N for like the number of hours. We got a 33.6 E negative KT plus C. Okay. Now, we don't know when that started though. I think the C is what, 65? Well, we know at 8 p.m., right? At 8 p.m., the temperature was 83.1, so maybe we can use that to solve for K. Confirm that it works for an hour later, and then we can figure out what that works, what that gives us when the time was 0. Let's see if that works, right? What's the time? All right, let me check one other thing. So I think we got that. That's fine. The value K must be found using the two temperatures. That's fine. Number of hours and K. Oh, we're still trying to solve for N. Okay. Okay, that's fine. That's the N plus 1. Okay. All right. Let's see some. Again, that just stands for like the number of hours since the murder. Okay. So then for the first one, right, we get this 33.6 E to the negative KN, right? We're trying to solve for K. We don't know how many hours it's been, but we know that that temperature at 8 was 83.1. And then, like I said, 1 hour later, so we do the 33.6 E to the negative K times N plus 1, because it's been an hour later, plus 65. That temperature was 79.4. Okay. So now we have two equations and two unknowns we should be able to solve. Okay. All right. So let me see. What's the best way to go about this? I'm going to kind of work them simultaneously. I'll subtract 65 from both. Let me see. Let's try to finish this. Okay, 83. Hopefully my numbers are good. 83.1 minus 65. So we get an 18.1 there. Okay, 79.4. 14.4 for this other one. Okay. We still got our 33.6 e to the negative K times N plus 1. We can divide both sides by the 33.6 on both sides. I mean, for all equations. So the first one will get e to the negative kn. I'll just leave it as 18.1 over 33.6. The second one, we get an e to the negative kn plus 1, 14.4 over 33.6. We could take the natural log on both sides. Okay. On the left, again, what I'm doing here, natural log of this is going to come down. Natural log of this, just leave it like that. Same thing here. Natural log of this, okay? So now we have a negative kn equals natural log of 18.1 over 33.6, negative kn plus 1, natural log 14.4 over 33.6. We could get both in terms of k. Like we could solve for k in one and use it in the other. Does that help us? Sure, I guess. Okay. So from the first one, we get that what k equals natural log 18.1 over 33.6 divided by, we could put a negative here, this in, and then we can take that and plug it into the second equation, right? If we do that, it looks like we get a double negative, natural log 18.1, 33.6 over n times n plus 1 equals natural log 14, can't write today, 14.4 over 33.6, okay? So if we distribute, it looks like the ends are going to cancel for the first one. So we'll have this natural log 18.1 over 33.6 plus natural log 18.1, 33.6 over n equals natural log 14.4 over 33.6. I think we're in the home stretch. I think we're there. Okay. So on the right, we're just going to get some number, right? Natural log 18.1, 33.6 over n. We get this natural log 14.4, 33.6 minus 18.1, 33.6. I know I'm not writing well. I'm just trying to finish. And I guess you could cross multiply. Long story short, we get the n equals, on bottom, we have this natural log 14.4, 33.6 minus 18.1, 33.6, all under 18.1, 33.6. Okay, so that's an exact result. Then we need to crunch this to get an expression for n. And then once we have n, we could probably solve for k from there. I'm gonna get a copy of this. We got like less than 10 minutes. I'm just trying, like I said, I'm just trying to get you guys out of here at this point. Let's copy. Hopefully we don't lose our question because sometimes we take too long. Okay, let's crunch this and see what happens. This is gonna be do or die. If I get it wrong, then I'm just gonna scrap it. Like, you know, we'll see how if we can troubleshoot it. Okay, natural log 18.1 divided by 33.6. All of that divided by, now bottom we have this natural log 14.4 over 33.6, okay? Then we got to say minus the natural log 18.1 over 33.6, okay? 33.6, that needs to go like this. Close off the denominator. So for n, we get something like this. I'm going to store this as alpha n for reference. Okay. So we get that n, oops. N is approximately, I'm going to write out the long decimal, 270, 51, 07, 723. Okay. And then if that's N, then our K is going to be approximately, we're going to say negative natural log of 18.1 over 33.6 divided by alpha N. And so for K, we get something like this. I'm going to write out the long decimal. 2286, 2286, 8373, 8373, 17. Okay. So we get that K. So we get about almost 3 hours earlier. So about 5 p.m. Let me see. If she got there at 8, 7, 6, about in the 5 o'clock hour. Right? Because we said N was the number of hours since the murder. And we basically solved the system of equations. All right, we got about 3 hours earlier. So in the 5 o'clock hour. Let's see. The murder was committed approximately, do not round to the front, then round to the nearest hour. So she got there at 8, 7, 6, 5. Let's go 5 p.m. Oh, that was an adventure, right? So, that one I just kind of went through it. We needed the right formula, which was Newton's thermal law of cooling or whatever, and so that C, it was basically exponential decay formula, and then the plus C factored in the temperature of the room, right? And so what that formula, the way we had it set up was that it was the temperature of the body since the hours, where N was the number of hours since the murder. So it's the temperature of the body based on the number of hours since the murder, right? So capital T of the N, again, capital N was the number of hours since the murder. So then you had to be aware that C was the temperature of the room, right? That was the room temperature. And then we know that, like, kind of want to just recap real quick. That was fun. I know that was a bit much, but right here, right? The C was the temperature of the room. We know that the normal temperature of a human body is 98.6 degrees Fahrenheit. So that's the initial conditions. So when the murder happened, the temperature of the body should have been 98.6. So then we can use that to solve for A to get our coefficient. That's just some coefficient in the function. It's not necessarily initial conditions, it's just a coefficient in the function that we can solve for. So then once we had our A, that's why she did 2 readings an hour apart, right? So because we had 2 unknowns. Every time you have an unknown, you need a piece of information. So at 8 p.m., she got the temperature when she first arrived. She waited an hour. She took the temperature again. So she had 2 pieces of data and she had 2 unknowns. So then when we put it all together, we had a system of equations and we had to solve for 2 unknowns. And we kind of worked the equations simultaneously, right? Again, we had our A. The first one, where N was the number of hours since the murder, that temperature when she first arrived was 83.1 degrees Fahrenheit. She waited an hour. That's where that second equation came from. So the number of hours plus 1, and then that temperature was 79.4. So then from there, it was basically algebra. I just did simultaneous algebra on each equation, subtracted 65 from both, we got a result, divided both sides by the 33.6. At that point, I started keeping it exact. Then take the natural log on both sides. Then we get this. Then I was like, okay, well, they both have K. So I solved for K in one equation and then plugged it into the other equation. And then that gave me an expression for N. I kept it exact. And then I only rounded at the N. So then once I had my N, then I went back and found K. We didn't even really need the K at that point. We just needed N. Once we had N, we had 2.7 hours earlier. So if she got there at 8, then that puts you in the 5 o'clock hour, right? So if you had some tapes or whatever, you would go look at 5 p.m. and then start watching to see who was there. And you can see it was Billy Bob. He did it with the night. You can see him on camera, or whatever. At least they have a sense of when it occurred. That's interesting. Like, if that's accurate, and these are all like approximation. It's not set in stone. It's like, okay, it still have to, it's approximation. Anyway, that was fun. And I've seen that one before. I think that when I worked at before, they kind of gave us a little bit more information or a different formula. But anyway, like I said, I was just trying to get you guys out of here. Let me see. So that was chapter 2, chapter 2 review. So again, next week should be our last week. Next Wednesday's our last live session. I'll update attendance. Again, your grades, I just realized that your grades should be updated in Blackboard. So Blackboard should have the most accurate representation of your grade. I would highly encourage each of you to check your grade in Blackboard for accuracy. Make sure that like the assignments that you've done are showing up, that it looks proper. If anything looks out of sort, just send me a text, or text is the fastest way to get my attention. And email is just for record keeping.
Hey,
Go ahead.
excuse me, Professor.
Yes,
What is the grade that we need to pass this course?
at least a 70.
All right. And is there any way we could do extra credit or anything to boost our percentage at the end of this semester?
I do have some tactics that I do automatically if I can do them.
All
Like,
right, because I'm trying to go back and do some of the assignments, but it takes off like 10% of the grade.
it's not gonna lower your grade. Even if you do an assignment late, it's not gonna. It only takes the highest score that you've ever got, right? So
But I'm saying I could only get so,
I know.
I can only get so high because it's taking 10% off, and my grade is not really going anywhere. You
Okay,
understand?
so for your grade to shift, if you want to see the shift in your grade, you got to maximize your exam scores. That's where because the homework and quizzes, that's a lot of work for minimal points. If you're really trying to like see an improvement, maximize those exam scores. Those that you get more bang for your buck with those.
Okay.
So
All right.
that's what I would prioritize. So between exam 1 and 2, I'll try to check Blackboard to make sure that it's clicking properly. But the bulk of the grade comes from exam 1 and 2, and then the final. That's the bulk.
All right.
Other
All right.
things are just for
And
practice.
then and then you said you might add some
Possibly.
extra possibly. All right. All right,
So
for sure.
so one extra credit that I might be open to is kind of automatic, and I do it if I can. It just depends on how the numbers fall. Basically, your overall My Math Lab score. Sometimes what I'll do is take that and scale it so that it counts as 10% of your overall grade. It's automatic. But it is a good idea, or a good thing to be aware of, that you know, okay, well, let me try to maximize my math lab score just in case he applies that extra credit. All right. So like basically what I'll do is whatever score you have in my math lab, I'll take it and scale it to 10%, provided it doesn't skew the grades too much. Sometimes it
All right.
does too much and I can't do it.
All right.
But for your sake, for right now, I would encourage you to prioritize those exams. Like try to maximize the scores as best you can, and you should see a change.
All right. Now I got you.
Yeah, that was a good observation. Any other points, questions? Hopefully everybody has done their course evaluations. Next Wednesday is the last day of class. That Thursday and Friday is the reading period. That following Sunday, which is a week from this Sunday, your final exam should become available. The hard deadline for all assignments is that Friday at the end of the week of finals. So that's Friday, May 9th at 11:59 p.m. I usually start pulling data to calculate final grades the following Monday after that Friday. So I kind of let the weekend play out, and then that Monday I start pulling things. Right. Any other questions going once, going twice? Forever hold your peace and rights. All right, guys. I'm proud of you guys. Good luck with everything. You know how to reach me, and have a great weekend. And we'll meet back on Monday to review chapter 3. Take care and peace. Thing is dying. I'm gonna plug it in. I need to do some paperwork, update attendance, check stuff. Anyway. All right, guys. Take care. That was good. I think the chat is okay. Let me check.